Hello everyone. So today I'm going to discuss a topic called sequences and series, and I want to do it a little differently. I don't want to do it specific to the topic that it comes in. In fact, I want to show you that this comes in precisely 3 places in the syllabus, comes twice in real analysis, and it also features in complex analysis. In real analysis, it features as a topic related to numbers as well as functions. Okay, so the beauty of doing it this way is that we see that even though syllabus sometimes can look humongous, it's not really that huge. If you understand the core fundamentals in one go, then you can apply the same knowledge in other aspects also, with slight difference, like just the application or just the look of it becomes slightly different. So let me start by defining what is a sequence. So real analysis or complex analysis both have this topic called sequences and series, but first and foremost we have to discuss what is a sequence. So the definition of a sequence in very simple plain words is that it is an arrangement of, it can be numbers, it can be functions, it can be objects. So it's as simple as, so for example, if you make a playlist of the songs that you hear or playlist of the videos that you watch, so it's like a playlist and it is written in a horizontal sort of manner. Of course, we can write it vertically also, it just space consuming. So we prefer to write a sequence as, so for example, if I'm talking about sequence of numbers, then I can write a 3, I can write a 13, I can write a 17, I can whatever. It just goes on and on. It may or may not have a pattern to it. Obviously, if it doesn't have a pattern to it, then it is what is called random sequence, and we are not really interested in that because we cannot predict what the next number is going to be. We don't know the nature of it and so on. And so usually the sequences that we come across have some sort of a pattern to it. And by pattern, we mean that we'll be able to judge what the nth term of this looks like. Very simple example of sequences that you must have done in school are arithmetic progression, geometric progression. So for example, if I write down a 2, 4, 6, 8, we can easily predict what the next element is going to be. All right. And also a sequence can be both finite and infinite, but finite sequences are not of very great importance right now because then they terminate somewhere. It's like they have a stop to it. So we're not interested in, mostly we are interested in infinite sequences, okay? And so this basically is an arithmetic progression with the common difference being 2. Then you can also have a 2 and a 4 and a 8 and a 16 and so on, where what is happening is that each element has a fixed common ratio with the previous one. So 4 divided by 2 is same as 8 divided by 4 is same as 16 divided by 8 and so on. So this basically is an example of an AP. This is an example of a GP. P means progression. So a sequence is also known as a progression because it progresses, you know. So a sequence in very simple words is basically just an arrangement of numbers. It can be, now if you come to higher maths, it can be arrangement of polynomials. So it could be x square minus 2, x cube plus 5, or it could be a arrangement of matrices. It can be an arrangement of anything. Okay, formal definition of a sequence is basically that it is a function. Now let's see, what does that mean? It's a function from n to say r if you're talking about real analysis. What does this mean? See, these elements are basically written as the notation that we use is A1, A2, A3 and so on. Here A1 basically stands for the element which features in the first position. Okay, so this basically is nothing but a short form for A at 1, or it is like the value of this function at 1 is nothing but A1. So it's a function from natural numbers. Natural numbers are occurring here. This is 1, 2, 3, 4th position, 5th position and so on. And what you are writing, so these have to be natural numbers. Now what you're writing in that position is going to be a real number if you're talking about real analysis, and it's going to be a complex number if you're talking about complex analysis. If you're talking about polynomials, then this can change to set of polynomials. If it is matrices, then this can change to set of matrices and so on and so forth. So formal definition of a sequence is that it is actually a function. Now, having said that, what is so important about this topic? Like, why do we say sequences and series is one of the most important topics of real analysis? What we want to discuss about this sequence is the behavior of the sequence, and specifically what I'm referring to is the definition of or the meaning of this sequence being convergent. So you see, the maths that we do also like heavily depends on the language, right? So English word converging, and if we take it up as a definition here, what we're trying to say is converging. Generally, what does converging mean? Going somewhere, right? So when we talk about a sequence being convergent or the convergence of a sequence, what we mean is that these numbers a1, a2, a3, a4 and so on and so forth, the infinite ones, are they specifically approaching some number, say L or not? For example, if I write down a 1 and a half and then 1 by 3 and then 1 by 4, 1 by 5 and so on, and you use the number line to mark these points, and as you can see, the first element is going to be here, which is 1, then it is half, then it is 1 by 3, then it is 1 by 4, then it's 1 by 5, dot, dot, dot. As you can see, the pattern of these numbers is it's never negative. So it's never going to cross the 0. However, the numbers are becoming smaller and smaller. So 1 by 5, 1 by 6, 1 by 10 becomes like a 0.1, 1 by 100. There'll be some, and then 1 by 1000 and so on. Where are these numbers going closer and closer to? So it's quite intuitive to see that 1, 1 by 2, 1 by 3, 1 by 4 never becoming negative, but slowly and steadily moving towards the number 0. In this case, we say that this sequence is converging towards 0, which is written with this arrow and 0. This 0 is known as limit of the sequence. So this L in general is called the limit of a sequence. This L is a number to which all these numbers are approaching. They are becoming smaller and smaller and smaller. Now, there are many aspects of this that can be discussed at length. Today, of course, I'm not going into the details of it, but we can show that if the limit exists, then it is going to be unique. Mind you, I did not say limit always exists. I'm saying if the limit exists, then it is going to be unique. Again, there is a theorem behind it which can be proved very logically. Maybe we can take it up sometime in future. But this limit, if it exists, is going to be unique. Let us try and formulate the formal definition of this, because that also students generally find it tough, and it's that famous, very, very famous Epsilon-delta definition of convergence. Now, what is this epsilon and delta? Till now, what we were trying to do is formulate it with the help of an example. So visualizing it, where is it going and so on. Now we want to generalize it. So if you have A1, A2, dot, 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 and you're saying that it's converging towards L, what does it technically mean? So let me try and give you a background for this definition. That when you're saying they're going closer and closer to L, that means the distance between them is becoming smaller and smaller. Smaller and smaller. As you can see, if I refer to the example above, why are these elements going closer and closer towards 0? Because the moment you go ahead, like if you progressively move your hand to the right side, if you talk about this element, it's much closer to this as compared to the previous element, and is steadily moving towards it. Moving towards means the distance is becoming 0. Like I drew this number line also to show you how the distance is becoming smaller and smaller. But the distance, mind you, is never actually becoming 0. If you look at this element, there will be an element called 1 by 1000. This also is away from 0. So this is 0, so this is, if you magnify it, then this is say 1 by 1000. The distance is not really 0, but the distance is becoming smaller. Now go ahead, the distance will become even lesser and lesser, but won't really. None of these elements here have a 0. If you write down the nth term of this, it will be of the form 1 by n. So none of the terms is 0, but they're progressively moving towards 0. And moving towards, like I said, means distance is becoming smaller and smaller. And distance, like in this diagram, I'm moving towards 0 from the right side. I can also move towards the limit from the left side. So the distance becoming 0 has to be written in a formal way. And how is that done? So how is distance measured? Let's see that on the number line. If you have, let's say 2 here and 10 here. So I've marked 1 and then 3, 4, 5 or whatever. Then the distance between these 2 points is calculated by subtracting them. So the distance is going to be 8. If you see the distance between 1 and 2, for example, then you will not say that the distance is -1. You will still say the distance is 1, because distance is a positive quantity. You have to remember the distance cannot be negative. Okay, so basically you're only interested in the magnitude of it, you're not interested in which side. And therefore, the generalization of this is, if there is a point called x and there is a point called y, and you have to take the distance between them, you have to take the difference between them, that is x minus y. But in my example, y is bigger, so you would say that, ma'am, it should be y minus x. So let me write x minus y and then put a mod in front of it. So mod is basically the way distance is measured between x and y. Okay, keeping this review in mind, the meaning of the sequence converging towards L means that the distance between AN and L should become smaller and smaller, lesser and lesser, but never really zero, as we saw in this example. So the distance is measured keeping the quantity epsilon in mind. So what is actually epsilon? Epsilon is a small quantity, a very small quantity, and small is a relative term. So we can discuss this more in detail, but let me quickly just help you formulate the definition that this distance has to become lesser and lesser and lesser. Lesser than what? Lesser than any predefined quantity called epsilon. So you have given me epsilon in this case as, for example, 0.01. Okay, then you see the distance between 1 by 3 and 0 is not less than this. 1 by 5 and 0 is not less than this. You go to 1 by 100, the distance between 1 by 100 and 0 becomes exactly 0.01. However, after this, all the elements that you have their distance less than the fixed quantity that you have given me. So this epsilon is basically a quantity which is free to take any value. It's usually a very small quantity, but this does not have to happen for each n. It has to happen after a particular stage. There is a particular stage after which the elements are so close to this number that you're calling as the limit, that is, it is almost impossible to bifurcate the two. There is no way you can split them up into two different places. So the formal definition of convergence becomes that the sequence A1, A2, dot, dot, dot is said to converge towards L if and only if, for no matter what epsilon you give me, that is for each epsilon greater than 0, there exists a stage, say n naught, belonging to n. So for each epsilon greater than 0, there exists n naught belonging to n, such that the distance between an and L becomes less than epsilon, and this has to happen for all n greater than equal to n naught. So this is a very, very, very important and a crucial definition. And it's not really abstract, but this is where real analysis starts to become slightly tougher, because this leads to a whole lot of theorems. It leads to understanding that if you have a sequence, say A1, A2, dot, 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 converging towards L, and you have another sequence, say B1, B2, dot, 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 say converging towards M, then their sum, that is A1 plus B1, A2 plus B2, and so on and so forth, would also converge. Not only converge, it will converge to L plus M. So this is basically known as sum theorem. So this leads to the whole series of theorems based on what is known as algebra of convergence, sum theorem, difference theorem, there could be product theorem. So it basically helps us to analyze, and if you look at the word analysis, it helps us to analyze the behavior of these sequences, okay, whether they are going somewhere in particular, are they going to give you a finite looking sort of an answer. Surprisingly, this also has applications in differential equations, and it's fun actually to see how real analysis and complex analysis are related to differential equations, even though none of the books would directly mention it. It's not a prerequisite also, but it's important to see that the solutions that we get in applied maths need to be convergent, need to have a meaning, otherwise they just go towards infinity. And they're not practical solutions to the problems that are posed to us, right? So this is a definition of a sequence, and as we were discussing, this is what a sequence looks like. Very important concept, that of convergence of a sequence has been now discussed. What I would like to do from here now is to show you the little bit geometrical interpretation of this, because it really helps us to understand how does this really look like in terms of a diagram. So I hope everyone recalls, and let's do it as a review, that if I talk about mod x less than a, those numbers whose mod is going to be less than a number, say a, then this boils down to the x's which lie between minus a and a. Mod x less than a basically means x is between minus a and a. So analyzing this part of the definition with help of this means that an minus L has to be between minus epsilon and plus epsilon. This has to happen for all n greater than equal to n naught. This in turn means an is between L minus epsilon and L plus epsilon. And if you look at the diagram of this, there is a number called L, which is, like I said, the limit of a sequence, and epsilon is some quantity. But whatever quantity it is, L plus epsilon, because epsilon is a positive quantity. Remember, it measures distance. So L plus epsilon is going to be somewhere on the right side, right? And L minus epsilon is going to be on the left side. And this distance has to be same as this distance because it is epsilon. This is the epsilon distance that you have. And what this definition is telling us is that after the n naught stage, all the elements of a sequence, remember sequence is infinite, so after n naught stage, so after the 10th or after the 20th or after the 30th, when I say something like that, I mean infinite number of elements, right? Infinite number of these elements of the sequence lie between L minus epsilon and L plus epsilon. All of them are sort of clustered around this, okay? Now these words called cluster, there is a definition of cluster point also. Like I said, we heavily depend on English language to formulate these definitions, but we don't just arbitrarily pick up the words. They have to have, in context of what we are talking about, they are related. So it's actually fun to look at every definition from this point of view, that why are they called cluster point? Why is it called limit point? Limit because it's limiting, no? The elements are not allowed to go beyond the fixed L minus epsilon and L plus epsilon. And so the definition looks like that there is this open interval that you have, and all the elements of the sequence, by all I mean infinite number after the n naught stage, are all lying here. They're all clustered around this particular point. So this is how the geometrical interpretation of a convergence of a sequence looks like, okay? Now let me take this definition first to show you how it is going to come in complex analysis. So how is it going to look like in complex analysis? So we will just copy the definition right now, okay? Because I want to just show you the connection between various things. So I have replaced, remember what I had written on the previous slide was A1, A2 dot 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 converging towards L. And this was in real analysis. So these are real numbers. This is a real number. Now what I'm doing is the same definition. I'm basically, I've cut, copy and pasted in complex analysis. Now let's see what the definition looks like. So how it's written here is that AN sequence converges towards L, or it is also written as limit of AN as n moves towards infinity is L. This is the notation, okay? So here we say that the sequence Zn converges towards Z if and only if, copying the definition, for each epsilon greater than 0, there exists a n naught belonging to n such that mod of Zn minus Z is less than epsilon for all n greater than equal to n naught. Now as you can see, I've copied it verbatim. I have not made any change except for, of course, the notation. I'm using ZIs to say that these are complex numbers. Now, but the difference, look at the difference. One has to appreciate the similarities and the differences. So appreciate how this now looks like, okay? So I hope everyone can recall that when you write Z minus Z naught less than alpha, this is actually going to be a circle with center as a Z naught, this, and you're saying that the radius of this is going to be less than alpha. So when you talk about the interpretation of this particular thing, this now is going to look like this is your Z, and the Zns have to be This does not open up like this, okay? This actually means that ZNs have to be in this circle whose radius is going to be less than epsilon. ZNs have to be, because remember complex analysis is like R square. Another interesting way of looking at complex numbers. But instead of this interval, it gets translated to this circle. So the elements have to be all in this particular circle which has a radius which is less than epsilon. So see how beautiful. This has extended to give you this particular definition. In fact, it is because of this definition that epsilon here or here also is given the name radius. Even here, when we draw L here, L minus epsilon here and L plus epsilon here, this is known as the epsilon neighborhood, or it's known as a neighborhood which has radius as epsilon. Radius word doesn't make sense here because it is actually only one single line, but the word radius has been inspired from this particular definition. So now you see how, I wouldn't say they're identical, but there's a lot of similarity between the two. So we learn how to appreciate the similarity between two things and then look at how they are different. Then it makes the story complete. So first appreciate the similarity so that you know at least the basic fundamentals about it. And then you look at how they become different from each other. Very quickly now I'll show you in the syllabus where this comes for the third time. So 2 times, one in real analysis for numbers, one complex numbers. Third time it comes as a sequence of functions. Okay. Now when it comes to sequence of functions, so now I replaced AIs by ZIs to show you in complex. Now I'm replacing them by FIs to show you that this is now a sequence of functions. So if you have F1, F2, F3, ... converging towards F, this is also an arrangement of functions, so it's a sequence of functions. However, the difference is that this is an incomplete story. You have to specifically write functions with their input. That means you have to write x also, as you all know. So f1x, f2x, f3x converging towards fx. Now, the difference is going to be there is not just one variable which is natural numbers or the position number. There is another variable called x. Therefore, for a sequence of functions, and I will not go into details today about that particular thing, this is a story for another day, that this has a meaning of convergence, but its convergence is divided into 2 types. One is known as pointwise convergence, whereas the other basically means uniform convergence. And why does the difference? Why is it not just convergence? Why is it pointwise or uniform? Because there is another variable to take care of, which is x. So if the convergence happens for each point, then it is pointwise. If for each point it converges, then it is going to be uniform. It might sound similar, but like I said, this is advanced real analysis. So first we will focus on basics. But when you come to this, which is, so if sequence of numbers is say chapter 1, then this is chapter 5. One has to do chapter 1 completely and build up all the things that are required to be able to come here and appreciate it. Again, from exam point of view, there are many questions on uniform convergence that are asked over the past years. Sequences are also, of course, they keep asking. And so we will not go into the details of this. I'm just stopping here with regards to this topic, because otherwise it will become difficult. But there is another topic that is a direct consequence of this, and that is what I'll discuss in short now, series. So now you see so many topics, how they are interlinked with each other, and how beautifully they sort of, you can weave a thread around them to see that they're not really topic 1, topic 2, topic 3. You can actually merge them all together with basic core fundamentals in place. It's easy to appreciate higher advanced maths. So the focus has to always be on the basics. Now let's see, the topic is always called sequences and series. Why is it not called series and sequences? Because sequences is more basic. What do I mean by that? A series is actually inspired by a sequence. This is nothing but sum of all the elements. Again, when we talk about series, we always refer to a series which is infinite, because if it is finite, then we can always find the sum no matter what is the elements. So if I add 100 plus 200 plus 300 plus dot 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 till something 1000 or 2000, then I can get a sum. But if you add infinite elements, then this is basically known as a series, and we are interested in convergence of a series. But mind you, the word convergence has been picked up from sequences, but it does not have the same meaning. It can't, because here we don't have these elements separated from each other. It is not like a A1, then a A2, then a A3. It is the sum of all of them. Sum is one number, right? When you add a lot of elements, you'll just get one. So what is the meaning of convergence of a series? Even the word convergence is inspired from sequences, convergence of a series actually means that the series has finite sum. If these infinite elements added together give you a finite sum, then we say that the series is going to be convergent. At the onset, this sounds wrong. Infinite elements are added. How will their sum come out to be finite? But again, since your school, you would have seen that it's not impossible for that to happen. In fact, it happens more often than we may realize. Let me give you an example of that. So for example, if I write down 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 whole cube and so on. First, let me give you an intuitive way of looking at this. So there is a 1 and a half, that is 1.5. Then you add 1 by 4, then you add 1 by 8 and so on. You are adding, but the magnitude of the element that you are adding is progressively becoming smaller and smaller. In fact, if you look at this element, there will be an element called 1 by 2 to the power of 1000 something. The contribution of this term is going to be very small. And there are infinite elements. So more farther away from here you go, the elements become really negligible. So their contribution to the sum also becomes smaller and smaller. So this actually does have a finite answer. And what is the answer of this? The answer of this, by the formula of this, is actually an infinite GP whose sum is given by, it can be proven that the sum is given by A upon 1 minus R, A being the first term, R being the common ratio. So A is the first term, R is the common ratio, which you can see that this is going to become 1 upon, and the sum is actually 2. Surprising, right? Infinite elements are being added, but their sum just turns out to be a finite number. That is a definition of convergence of a series. Why is series studied immediately after a sequence? That will be my last point of discussion today, and I'm going to show you how series actually comes from a sequence. So let's see, A1 plus A2 plus A3 plus dot dot dot. If you want to know whether this, and now we're writing an arrow, but what we actually mean is that does it have a finite sum? Like, is it equal to, say, a number A, which is finite, or not? We're putting a question mark. How is the sum calculated? It's a very interesting exercise that can be done in the class also, that adding 10 elements, we can't add them together. We don't wait for those 10 elements to come. We add them two at a time. It's a binary thing. So A1 plus A2, then whatever you get, you add A3 to it. Whatever you get here, you add the next element to it. And that is actually the concept of sequence of partial sums, also known as SOPS, which is that if you're interested in seeing whether this has a finite sum or not, you just make an array of elements to which progressively you add one element. So just note down A1, then you do A1 plus A2, then you do A1 plus A2 plus A3, then you write down A1 plus A2 plus A3, like the previous one plus one more, right? And let's call them as, this is S1, this is S2. Look at the pattern. 2 means 2 elements are being added, starting from the first one, not any 2, first and second. S3 has to begin from the first, go till the third. This is your S4. If you can see clearly, the Sn here, the nth element, will come out to be a1 plus a2 plus dot 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 till an. And here, if I make n going towards infinity, if I don't stop at n, but let it go further and further and further, then this becomes the series that I'm interested in. See? If I make this n go towards infinity, then this becomes the left-hand side. And therefore, limit of Sn as n moves towards infinity is nothing but a1 plus a2 plus a3 plus dot dot dot. And if this limit exists, then this is nothing but sum of the series. So this Sn is known as the SOPS, and limit of the SOPS is nothing but sum of the series. If the limit exists, that is, if by the definition that we just discussed, if you have a limit for this, then the series is also going to have a finite sum, and therefore it's going to be called as a convergent series. And there are other two concepts which we're not getting into today, but I'm just mentioning for the sake of completeness, that apart from convergence, so there are three ways in which a series can behave. There can be convergence, divergence, and oscillation. So the way SOPS behaves dictates the way the series is also going to behave. So series can also be convergent, divergent, or oscillating. And it's very interesting that if you just have core fundamental sequences in picture, then algebra of series can also be taken forward from there. So the syllabus is not really humongous. You have to focus on the core fundamentals. Once the core fundamentals are in picture, then you can apply it to various things. Same thing I can do for numbers. Same thing I can do for something called double sequences. Then this SOPS also reminds me of something called FOPS, which is function of partial integrals, FOPI. It's also related to something that we've discussed right now. So the objective today is to just show you how the syllabus is actually interlinked. It is not one topic and then another topic is separate. They're linked to each other in a very cohesive sort of a manner. And once you understand one thing nicely and properly, then you can basically just look at the same thing in a different context and understand the theory better. So I hope it's clear, and I hope you benefit from linking the topics rather than looking at the topics separately from each other. Thank you.